Good morning. That's okay. I love it when you're chatting. It means you're happy to be here and see your friends. Good morning and welcome to the 74th winter season of the Los Altos Morning Forum. I'm Kathy Perga, your president. Are we okay, Dylan? I decided to greet you with Healthy New Year instead of Happy New Year because we all know that if you're healthy, you're happy. May I extend a welcome to our guests who are here. Please know that we are not an exclusive group. No, we welcome everyone. And if you'd like to join our distinguished speaker series, there are applications on the piano and in the back, and we'd be happy to have you. There are hearing devices available in the back booth, and they work. And speaking of hearing, let me remind you, and me also, to find your cell phone and turn it off. I see everybody reaching. At the conclusion of today's talk, we have a Q&A. And how it works for anyone who's new is you come up to the piano, you fill out a form with a question, and then our speaker tries to decipher your penmanship and reads the question. Our next speaker on February 6th is Rob Nichols. Rob is the nephew of Les and Anita Nichols. You know Anita was our past president. Well, Rob is the CEO of the American Bankers Association, and he will speak on banking. I think that's it. Okay, here's Ann Dewey to introduce our speaker.
Thank you, Kathy. And good morning to everyone, all of you who faced the rain and came in person. Your grit will be rewarded. And good morning to all of you, probably with your second cup of coffee, watching our live stream broadcast. To make up for remaining inside just now, I urge you to step outside after dark tonight and take a quick look at the night sky. How many of you have wished upon a star? Lots of people. How many of you understood exactly how far away that star was? Or what else might be out there deep in space? Nobody's raising his hand. Our speaker today, Garth Illingworth, has been answering questions about deep, deep space since before earning a PhD in astrophysics at Australian National University. That, by the way, will explain his accent to you. His postdoctoral fellowship was completed at Kitt Peak Observatory in Tucson, Arizona, after which he joined the Department of Astronomy at the University of California, Berkeley. From that point on, his career took him back to Kitt Peak and then on to the Space Telescope Science Institute in Baltimore, Maryland. Then he came back to California to the Lick Observatory in Berkeley. Subsequently, he joined the Department of Astronomy and Astrophysics at UC Santa Cruz. Then he went back to Perth in Western Australia, and by 2017, he was the Distinguished Professor of Astronomy, Astronomer Emeritus, Department of Astronomy and Astrophysics, University of California Observatories at UC Santa Cruz. That only tells you his academic titles and what part of the world what part of Earth he occupied. It doesn't tell you about the very long list of honors he earned. Those include recognition for, and I quote, path-breaking studies of infant galaxies at the dawn of the universe, lifelong service to the astronomical community, and astute guidance on the national and international scene. He has also represented NASA to Congress. But what really matters here today are his primary interests. Initially, he was interested in the very earliest galaxies, those in the first billion years of the universe. Subsequently, with the advent of more powerful telescopes, he became interested in the most distant galaxies. Illingworth was a pioneer in providing the rationale for the Hubble and subsequently the Webb telescope. It took 30 years, but when the Webb telescope was finally launched on December 25th, 2021, he was the last of the original architects still involved. He has also worked on the Keck telescopes in Hawaii and on the 30-meter telescope project, also in Hawaii. So, what does a famous, distinguished astronomer do when not examining images of deep space? He and his wife love to camp in wild places, in Alaska, in Africa, even in Yellowstone, to see the wildlife. So imagine looking at the night sky, past Twinkle Twinkle, and discovering a whole new galaxy. That's the work of today's speaker, distinguished Professor Emeritus Garth Illingworth.
Thank you very much, Anne. Thank you, Kathy. It's great to be here. Thank you all for coming out on another little rainy, warm morning in California, but we really need the rain, so that's good. You reminded me of something when I first started dating my wife of 55 years now. She was a primary school teacher in a country school, and she said, "Oh, an astronomer, you can come and tell me about the constellations." I said, "I have no clue about the constellations. Everything I look at requires a big telescope and is far too faint to see." So she was pretty disappointed. She thought her students already did better and knew more than I did about the stars. So anyway, I'm going to jump into what is one of the greatest science projects of all time. It's incredibly powerful. It's very expensive. We spent $10 billion on this with our partners, the Europeans and the Canadian Space Agency, and all done through NASA. And so I'm going to tell you about how this came about, how the James Webb came about, and show you some of the gamut of results. And so I will do that through the space of the talk here. So let me get into this. So there's a schematic here, but we'll see a lot more about James Webb. Oh, and by the way, I have to show you, I go all in on Webb. Here are socks with the Webb mirrors on. And of course, my golf shirt. So I've spent a lot of time on this, so I spent a lot of time thinking about it. So this is encapsulates what this is all about. It's about learning about our universe, about our origins in so many ways. Galaxies, stars, planets, life. And so the Webb can touch on so many of these things, and I will come back to this later. But I always think of this as our infrared Hubble on steroids. It is immensely powerful. Hubble has been amazing. This has taken us into a whole new regime. So this was the very first image that was shown. This was actually revealed at the White House on July 11, late in the afternoon, with the president and vice president who saw this and asked some questions about it. And so this is an incredibly deep image of the universe. What's amazing is it didn't take very long. Webb spent 12 hours on this. I worked on projects on Hubble where we spent hundreds and hundreds of hours trying to do this, and we did it. But this is sort of 50, 100 times better than Hubble for doing a lot of this work. So we're in a whole new regime with this. So what I want to do is I'm going to talk to you up to the launch in Christmas Day and the first image release, which you've just seen. I'll come back to that later. So really the lead up to launch and commissioning, and then back off 35 years to tell you about how we started Webb and why we started it, and then more about the amazing technology in the telescope, and then give you some sense of the science results at the end. So this is Webb. We will never see Webb as it actually looks. It's a schematic. We have never seen the whole telescope. We could never do that on the ground. There was no way we could actually release everything and make it the whole telescope. I'll show you some things that are close, but this is what it looks like schematically, and I'll talk through more of this, but it really has a hot side and a cold side, and I'll explain why that's the case. By the way, the mirror is 21 feet across. This is big. Those sun shield is the size of a tennis court, so this is a huge facility. So with a little more detail, don't worry too much about some of the numbers and things here. As I said, there's a hot side and a cold side. And so part of this, the hot side, the communications, the power, a lot of capabilities, they're all face, the computational capabilities, etc., all face the sun all the time. And on the other side, the telescope and the instruments are actually radiate out into space and cool down dramatically. And that is absolutely crucial to make this really sensitive in the infrared, the longer wavelengths. And so, again, I'll show you a little more of this later. But now to give you a better sense of the scale. So this is in the last few months before Webb was shipped out to the launch site. On the right is where it's all folded up, ready to be shipped and ready to be put ultimately, as you'll see, into the rocket, onto the rocket. And so that was in August of 2021. You can see how big this is. The folks there in the bunny suits in the clean room look pretty small against Webb. So on the left, this is the best that we ever saw in terms of seeing the whole telescope on the ground. We couldn't open out two of the wings on the mirror. It was just not possible to do, or pull down that other mirror at the top of the secondary. But still, you get a sense again of the huge scale of this project. So then, of course, it was in Los Angeles at Northrop Grumman where it was put all together, and it had to get out to the launch site. Now, the launch site was in South America. We had, as I mentioned, the European Space Agency was a partner here, and so the Europeans had agreed to launch it on the Ariane 5 rocket, an amazingly good rocket. And so we had to ship it to the launch site. So it was packed up and put in a special environmental chamber on the truck there. The truck and the chamber and the telescope all went on this specially modified boat that the Europeans used to ship things out, taken through the Panama Canal. There's an interesting story here. NASA did not, because this is a $10 billion piece of hardware being shipped out, NASA was cautious about what they announced about this. But folks had found out the ship that it was on so they could track it, of course. And so they found out when it was going through the canal, and somebody dug up this footage from the canal showing the MN Calabre taking taking Webb through the canal there. So that ship with the red arrow there is it on its way. Then it gets to South America, to Guyana, French Guiana, and that is where the Europeans have a huge launch site. So it's taken off the ship there, and then the container is taken into the launch site. And then it has to be there for several months while it's prepared to go on the rocket. And so the next one, when it comes up here. So here it is as part of the preparation process. On the left, those guys there in those elaborate suits are actually handling some very dangerous chemicals, the propellants that go on board the Webb that actually help move it around and help get it out to the place in space that need to be 1.5 million kilometers beyond the moon. And then on the right, when everything was loaded up and it was checked out, it was picked up by a single steel cable and lowered down onto the rocket. Every time I saw the cranes pick it up with one steel cable, I was really nervous. But of course, every time was okay. Of course, they engineer these very well, but I get nervous with just a single point failure. You'll see more of that later. We have a lot. So here it is on the left. It's being put on top of the rocket, and the shroud is being put over the outside. And then the rocket is finished up it was basically ready to go at that point, all fueled up and everything. So then it was moved out onto the launch pad. And this was done, I think, Thursday night, just before Christmas. Christmas was a Saturday in 2021. And I was in Baltimore, Maryland. I wasn't down at the launch site. Some people were, but most people were not. It's hard to get down there. So ready to go at the launch pad. And so then let me see, there we go. Christmas morning, 7:20 a.m., Webb launched from that pad. I was at Space Telescope Science Institute, and they had these giant cookies, which were really good, actually. They were nice butter cookies, and on them they had little plaques or little pasted things about the science goals for Webb. So that was sort of a cute little memento. I still even have a few of these. I wouldn't let Wendy eat all of them. She really liked the butter cookies. So this was an amazing launch. It was meant to go at 7:20. I think it went at 7:20 to the second. And then we were listening to mission control in Kourou, and the French director, control director, was sitting there, and about every 30 seconds or so he'd say nominal. And it sounds sort of, what the hell does that mean? But in the space business, this is crucial, because nominal means everything is working perfectly. And it was just nominal. And then 30 seconds later, nominal. And we're all going, whew, thank goodness. So that was an amazingly good launch. And so at that point, we were waiting several minutes to get it up into orbit. And we were lucky here with this telescope, because ESA had planned for its new rocket that they are putting together now to put a camera on the top to see how the payloads eject. And they decided they would bring it forward. Arianespace worked with them, the company that builds the rockets, and actually put a camera there so we could see JWST moving away. And the next video will show you this happening. And so what you'll see here initially is Webb is still attached to the telescope, and this big fuzzy blob with all its insulation, and then you'll see it sort of jump away. So here it is right on the top of the telescope still, and there are large springs at release point. They push it away from the rocket so that it separates from the upper stage. And so at this point, Webb is moving away. We're now, as you can see, that's still close to the Earth. Webb is being set up now to head out beyond the moon. So the rocket was planned to point it at the trajectory it needed to get out beyond the moon. And 1.5 million kilometers, 1 million miles beyond the moon is where it goes. And we were all sitting here watching this, and we knew that we wouldn't be able to see it for very long. As you'll see a little later, it moves away because the rocket upper stage is designed to go away from Webb. But one of the crucial things is it has solar panels, like everything we use in space, and batteries. So it was operating on batteries at this point. The batteries can only last for hours. So it was absolutely crucial that the solar panels came out. And we knew that the solar panels were going to come out at 6 minutes. So we were all sitting here, oh, we're not going to see that. And so we were watching it, thinking, oh, this is great, it's on its way. Solar panels will come out in a few minutes. Hopefully, we absolutely have to have that, otherwise we have a dead telescope. And suddenly, the mission controller, the announcer of mission control said, no, the solar panels are coming out. And we all thought, well, that's great, absolutely great that it is happening and we're going to get solar power, but why are they coming out so early? So I actually saw the systems engineer for Webb, who had been working on it for 10 years. He was a good colleague and good friend. And I said to him after this event, So why did the solar panels come out at a minute or so? And he said, beats me. So I thought, okay, that's interesting. The system engineer isn't even sure what was going on. So you can see at the moment the Webb seems to be drifting, and that's because the upper stage is turning away so as not to follow it. And so it turned out later, of course, what happened was that Arianespace had so precisely controlled its rocket burn and position and orientation that when the onboard software that releases a solar panel looked and said, well, do I need to move the spacecraft to be in the right position? It said, no, I'm perfect. I'll release them. And it did. So the French rocket folks did an amazing job for us. And there's another part which I'll mention too, about where they really helped us on this. So at that point, we were headed out past the moon out to our orbit. And of course, we were all folded up. So we had to unfold things in space. This was crucial and nerve-wracking, this first 15 days. So big pallets came out which have the sun shield on them. The sun shield's pulled out, very flimsy materials. You'll see that later. Separated, so we had our 5 layers as needed. Then, of course, the wings have to fold in from the mirror. The secondary has to fold out. So all these steps had to happen. Actually, there were a lot more as well. So those steps, first 15 days, that went well, thank goodness, because anything that didn't work then meant that we had a piece of space junk. It wasn't a telescope anymore. And then we had another 10 days where we had to move all the mirrors into the 18 mirrors with their incredible actuators right into position. So any one of those that had not worked, 132 actuators, would have been a problem for us. But at the end of this 30 days, we were in great shape. The telescope looked good. And that all happened so well. As it says here, there were 50 major deployments in this whole process. There's 280 potential single-point failures on this mission. And a lot of actuators that release things and let things move or push them out. Every one of those worked. And if one of those 280, and in particular 178 non-explosive actuators had not worked, as I said, we wouldn't have had a working telescope. So we call these single point failures, and they are nerve-wracking. There's no option. They just have to work, and they all did. So we were very happy at the end of this phase. So where are we? We're at this point. So what's happening out there? So Webb is being deployed and is now a telescope, but it's still actually moving out towards this position in space where it sits. And it sits, as I mentioned, 1.5 million kilometers from Earth, beyond the moon. And it's a wonderful place for a telescope. So there's a sort of schematic here. So it leaves the Earth, just is shot out beyond the moon, and it has to get to this location we call a Lagrange point, where there's a stable gravitational field, and you can actually orbit the telescope around this point in space. There's nothing there, but because of the Earth and the moon and the sun, there's a gravitational sort of sink there that it can move, go out and move around. And you'll see there's a nice little video that shows you how it goes around the sun with the Earth and moon. Getting it there was tricky because we had to very carefully take it out, move it out, and put it into the orbit. So the rocket positioned us well, but we had to then do additional propulsion moves to make sure it was going exactly right. And then when we got out there, we had to shoot it into an orbit around this L2 point. They were potentially quite demanding of the onboard fuel. And so the tanks were sized to allow us to do that and to allow 5 years of life, which isn't very long actually for a telescope like this. So we always had a goal of 10 years. So because Arianespace did such an amazing job of positioning us both in velocity and in direction, we actually didn't have to do very much in the way of using up the fuel in what was called the burns. That there were 2 of them near the moon to get us out there, and the one that into the orbit was relatively small also. And this was important that this be done very precisely, because if the burns were just a little too strong and we overshot L2, that was it. We could never come back. It's impossible to reorient Webb and come back. So there's a lot of precision required here. And it went so well, in fact, that we used so little fuel that we have over 20 years of life. In fact, some folks think we might have nearer 30, so 25, 28 years of life. It's amazing, actually, how well we did. We really owe it to our European colleagues for their incredible rocket. So here is a little video that just shows Webb in its orbit around this point in space as the Earth and Moon move around. So if you look near the Earth, the blue thing, there's a little moon going around there. And so then Webb is going around with the Earth, always 1.5 million kilometers, 1 million miles from Earth. So this is a wonderful place. We always can communicate with it. You notice in that orbit, it never is shielded from the sun by the Earth, which is very important. Actually, I might go back and just play that again. It's a good little video. Let me see if I can get back to it. Yep, there we go. So it gives you a real sense of Webb out there moving around with us as we take our yearly journey around the sun. And it's taking its sort of 6-monthly journey around this L2 point, always in communication with us and sending back tens of gigabytes of data every day through the Deep Space Network. So here is a little better definite or clarity on what's happening with regard to how this telescope is heated. So you see where the sun, this is big. So the sun is putting 200,000 watts of power into thermal power into the hot side. And we have to make sure that there's no more than a tiny fraction of a watt, an LED flashlight worth of heat that gets to the other side. So these 5 panels of very flimsy aluminized material are what do that. They stop that heat being transferred. And in fact, if you work it out, it turns out the SPF of the sun shield is about 1 million. So it's a pretty good solar inhibitor, as it were. And what's happening behind is that the telescope is looking out to space. Space is a few degrees Kelvin, a few degrees above absolute zero. It's incredibly cold. So the universe is a giant refrigerator for this, and it just cools down. And it just cooled down to about 40 degrees above absolute zero. And that gave us the opportunity to have incredibly sensitive instruments in the infrared. So I told you that we had a month, we got out there, but getting this telescope working and calibrated and operational was a big task. There was actually another 5 months of activity. And so there's sort of lots of detail here, but the main thing is that it was a hugely complex task. There was a giant spreadsheet which had 700, that was divided into a series of major steps, and that was all then subdivided into yet another series of steps that has to be carried out, cross-checked, verified. So it took a long time, but the optics were tuned up, the instruments were all checked out, and then the first science images were obtained. So that was what happened in the next 5 months. And none of us, except for a very select group of people at Mission Control, actually could see what was going on. NASA released a little information, but they didn't like to release too much. So, whoops, I went too far. So the commissioning period ended at the end of June last year, 22. And so the optical performance of the telescope was amazing. We had set a requirement, and we were actually twice as good as the requirement, which was sort of a goal that we had, but that's an incredible difference in terms of optical performance. The instruments were performing extraordinarily well. They were at least at the level of requirement, and actually in most cases were more sensitive. And so at the end of this, Webb exceeded its requirements and basically met its goals, and in some cases exceeded its goals. So it worked, and it worked extraordinarily well, which, as you will see a little more, as you start to see some of the construction steps here, this is a very complex telescope. So I wanted to back up at this point and give you a sense of what it took to start an endeavor like this. You know, we often have ideas about what we'd like to do, and sometimes we get lucky and they actually come to fruition. So this started like, whoops, I double hit again, like 35 years ago. So we had a very rough concept, and we thought that a big new telescope to follow Hubble would be a great idea. And why did we think we needed to do it 35 years ago? Because Hubble wasn't even launched at that point. And so this is a comment I heard one morning. Start working on the next big mission. It will take a very long time. And he was right. So Riccardo Giacconi, I was Deputy Director at Space Telescope Science Institute at this time. Riccardo Giacconi was the director. He subsequently got a Nobel Prize for his work on X-ray telescopes. And so he had a lot of experience doing some of the early missions, and we'd been working on Hubble for a long time. But we knew it took a long time. He said, "You've just got to start now." And I said, "But Ricardo, Hubble's got huge problems. We're all up to our eyeballs trying to solve those. We don't have time to think about the next mission." And he said, "Trust me, you really should." And since he was director, I sort of, "Okay, Ricardo, it sounds like we should." So several of us got together and started to think about what we should be doing beyond Hubble. And we came up with this concept that we called the Next Generation Space Telescope, and particularly that it worked in a different regime, longer wavelengths, using very new technology, which was just on the horizon at that point. And so we started putting that together. And here are the folks who did that. So Ricardo is here outlined there, the director. There was sort of this group of 3 to 4 of us, Peter Stockman, myself, and Pierre Boully, an incredibly good engineer, French engineer. So I actually saw Pierre in Paris about 3 weeks ago, and we had lunch together. That was good to do. So this is what we were doing. This is fascinating, actually, to think about. You are building one of the most powerful telescopes that has ever existed. You are building the most powerful telescope that ever existed at this time. That's Hubble. So now we're thinking about what could we do that would take us way beyond Hubble. So we think of this as conceptualizing what comes beyond Hubble before Hubble. That was an interesting issue. So we had to think about what Hubble would never be able to do. And that's where we came to think about this whole new regime in the infrared at longer wavelengths than what Hubble was working. And so that basically guided the effort for several years there. We had a big meeting at Space Telescope Science Institute, sponsored by NASA and STS and Space Telescope, thinking about the science, thinking about the technologies that were needed. This meeting occurred before Hubble was launched also. So it was very much thinking into the future. The following year, and every 10 years, the astronomy community does a big study and evaluates what it wants to do for the next 10-year period or longer, because typically these missions take a long time. So there was a panel that was working on thinking about space telescopes, and one of the recommendations this panel came up with was to do a 6-meter telescope, sort of like I've been talking about, like the NGST. That was an interesting thing to do, but because we hadn't gone very far into it, the panel that makes the final decisions, our sub-panel reported up to the bigger panel. They said, "No, it's too far in the future." And so we won't accept that. We'll do some of the other projects we really need to do. But we sort of got it on the stage, and we made a cost estimate. We thought it'd be a couple of $2 billion for this 6-meter. That was part of that step. We had a big technology meeting that was sponsored by NASA headquarters and carried out through JPL, where again we were focusing on this large infrared telescope, 8 meters, 28 feet, I think, 26, something like that at 8 meters, very cold. So the same things that we've been talking about, but now looking more at the technologies in the 90s. So this was really the genesis of JWST, the James Webb, and at that time it was called the Next Generation Space Telescope until 2002. A few years after this, Hubble was launched in 90. It was fixed in 93 from all its optical problems, and this image was taken of the sky. This was absolutely remarkable. A lot of astronomers thought it was a complete waste of time to spend 10 days looking at a blank patch of sky. When the image turned up and it was just packed with galaxies, far distant galaxies, everybody realized that this was something that Webb could really do. And so it took 10 days on Hubble. Webb can do this in 6 to 7 hours. So that sort of set the stage then for the work that would subsequently be done with thinking about Webb, that the science would really be focused initially on these distant galaxies. 2 big studies were done in the 90s, looking at different missions, different concepts, and different sizes of missions. The NASA administrator at the time, Dan Golden, was just a great guy with a lot of vision. And he took the recommendations and carried it forward and said, we really should be doing an 8-meter. And that helped us greatly. But of course, we had to make sure that the science community was really on board with this. And so the next decadal survey was coming up in 2000, and they top-ranked this project, said NGST is #1. This is what we want to do. And so, and focusing on the science of the first galaxies. Unfortunately, they said probably it will only cost $1 billion. Now, this was partly Dan Golden. Dan was very visionary, but he really wanted to make things faster, better, and cheaper. Well, you can pick any two of the three, I think, but you don't get all three. So he said you can't spend more than $500 million on construction. So we started out with a budget of about $1 billion. And remember, in '90, we thought that a smaller telescope was going to cost $2 billion, or roughly $3 in current dollars. So, boy, I was nervous about this. But anyway, I was just glad if we could move forward, and then we'll sort it out. So then we got into a phase of construction. And so how did we get to the launch and first images? 22 years later. Why did it take so long? Well, it was slow, it was painful, and we sank a huge amount of money into this. But all along, I have been impressed with the capabilities, the dedication, and the willingness of people to solve problems and just get in there. Great crew of people, 20,000 people across the country, across Europe, and in Canada have contributed to this telescope through companies. It's a major set of people, a lot of capability there. So we realized that 8 meters was probably too big, took it down to 6.5 meters as the goal there, and then selected the contractor who was going to be the prime contractor for this, Northrop Grumman, and it was renamed the James Webb Space Telescope in 2002. So then we started on this path where big project, not enough money. And this was a problem. So a new NASA administrator, Mike Griffin, came in the middle of the decade, and for years Webb had been having budget problems and being a problem for the agency and Congress. And so Mike inherited this mission. And, he just said, oh, you guys, you undercosted this. It was sort of an invented word for him, but it was exactly right. So we were at the point where every year the budget requirements went up. They had to go to Congress, they had the administration support, go to Congress to get the help to do that. But we could never get over the top of it. Every year some new problems would arise. So by 2008, NASA held a very important review where we went into phase C, and they said, we think we can do it, $4 billion, 2014. And so within a year, though, unfortunately, this also became clear that it wasn't going to happen. So the administration, the Office of Management and Budget, was getting very unhappy about the continual requests from NASA for them to support a larger budget request to Congress. Congress was getting really unhappy because it kept seeing demands for an increasing budget. So Senator Mikulski from Maryland had been a great supporter of Hubble and then of Webb. So Goddard Space Flight Center is in Maryland. And she just loved the concept as well and was a good supporter. But she realized that it was in serious trouble in Congress. And so she sent a letter to the NASA Administrator Charlie Bolden, asking him or requesting him to set up an independent review panel. Of course, the word request was, yes, ma'am. So General Bolden did exactly that. So he set up a panel to look at what was going on, what had gone on and what was wrong, and what would get Webb into a situation where it could move forward and get to launch. And this had an extremely capable engineer who had led a lot of missions as a project manager from JPL. And it was a small group. We had to work extremely hard for a month or two. I was the only astronomer in the group. And so that was sort of provide that other access. And I was put there by the NASA administrator and Chris Scalise, his deputy. So we looked at this and we decided we were going to write a very hard-hitting report and just tell it the way we saw it. So we said that this was underfunded, did not have the budget needed at the start, that there were not enough reserves every year to deal with problems, that the technologies in some cases were being developed much too late while the mission was actually being constructed. All these are danger points. And what was really, I think, a killer for this program in terms of its moving forward in a well-defined way was that when problems arose, the project manager didn't have the money and NASA didn't have the money to fix it, so they would defer work. And the project managers on this group said, this will just wreck a project schedule, because when you defer work, you upset the schedule and you end up effectively paying 2 to 3 times as much to do that aspect of the project because of the larger hit than you would have had if you could do it with reserves right at the time it was needed. So we said, it's got to have a new budget. NASA really needs to look at this, but we gave an estimate and said we couldn't see it launching before 2016, and it was going to cost probably close to $6 billion to do. But NASA really had to do a proper bottoms-up budget estimate. So, of course, NASA, OMB, well, no, NASA had recognition here. OMB and Congress were really unhappy to see this report, but in some ways they felt that they got, a sense of what was happening and what was going to be needed. So, and NASA really stepped up to the plate and said, we support all the recommendations here, we understand the findings, we're going to move forward, we're going to do a really good budget and estimate. So we did. So this poor guy, Rick Howard, a good friend of mine, was brought in the day the committee finished essentially and said, fix this. It's your job at headquarters as program director. So he set up a process which is well established, starting to be established, I should say, at that time, to do a proper analysis involving the project, the contractor, NASA folks, and come up with a new budget. So in blue there is what Congress and OMB were expecting to see for the next few years for the budget. So the red is what they got. So there was, as I said, OMB and Congress were even unhappier than before. So this came out in sort of May of 2011. And then we got to this point where JWST effectively died. So the chair of the House Appropriations Subcommittee, Commerce, Justice, Science, said this bill terminates funding for the James Webb Space Telescope, $1 billion over budget and plagued by poor management. So this was a crisis. There was some sense in NASA that, Senator Mikulski will solve this, and she was in the Senate. This is a House action. I know we talked to a bunch of staffers and other people who had been through things like this, and they said, take it really seriously. There's no guarantee that even a strong supporter in one of the two houses can bring this back. So we got a lot of support from Nobel laureates, astronomers, but we also had astronomers who said, this should be killed. We want the money to spend on our projects, which of course is completely never going to happen. Congress, if they get money back, you're not going to get it. They have other things to spend money on. So commerce, justice, science. Science loses a bit of money because if a project gets cancelled, the money is almost certainly going to go somewhere else. So this was naive and very stupid of my colleagues, but it was a problem because they were going to Congress saying, kill it. So fortunately, we got a huge amount of public support. And I was astonished at this. This was years before we were launching this mission. And I think it was because Hubble had entered the consciousness, schools, and broadly across the US public as an amazing mission. And Webb was the next big thing we were doing in the step beyond. And I was astonished one day. I got an email from a teacher in Kansas who said, how can we help? What can I and my class do? That was so nice. So anyway, there was a lot of effort that went on for several months. And in the end, Chairman Wolf decided that, okay, there's a lot of support for this and a lot of discussions and negotiations with Senator Mikulski, some give and take, giving him some things he wanted, the usual congressional way that you deal with things that are done here. But I still think it was important to recognize that this really was on the cusp of being lost. Congress said $8 billion max, 2018 launch. And this is the Senator Mikulski and Chris Scalise at some point sort of celebrating this getting through. He was the director of Goddard, an incredible guy. very capable. So we got then into a more routine mode of activity, building up the mirror. So this was in 2016. The mirror and the instruments were all assembled at Goddard Space Flight Center in Maryland. And so at Redondo Beach, Northrop Grumman were assembling a lot of the satellite components and that sun shield. A crucial part of this next step was actually testing the whole mirror and instrument package. We didn't do that on Hubble. And for those of you who remember back to that day, Hubble had a serious optical problem. It's because we didn't test like this. So nobody was going to repeat the possibility of that. So a giant chamber was set up. The Apollo astronauts last used this in the 60s, was set up to test Webb. You can see how big it is. All those folks in their bunny suits standing around the mirror in the right-hand one there. So this is a big instrument. It went through the test incredibly well. The hurricane hit Houston in this period. The water, the whole facility was flooded outside. There was 3 feet of water around the facility. So folks were camping there trying to keep it cold, because if we'd had to heat it up because they didn't have the right coolant and things, it would have been a significant delay. So the team worked extremely well. In fact, they had to get a truck of nitrogen. They had to find some guy who was willing to drive a truck of liquid nitrogen through 3 feet of water to keep them cold, and they managed to do so. So people really step up to the plate when they need to. It's great. So here is this amazing sun shield. Tiny, thin material, a few thousandths of an inch thick, capped on and coated in aluminum and silicon material. So we have 5 layers of this incredibly flimsy material, and we had to deploy it in space. So this was a hugely challenging project, and Northrop did great on this one. I walked around the full-scale engineering model where they had made 5 layers, and they had it set up with the cables that they had to pull it out. And I thought, oh my God, this is never going to work. So they just tested and tested and tested. And, they really got it to come together. So this is an engineering feat, I think, that's one of the most remarkable of this whole activity, dealing with this very flimsy material. So here is their tested flight. This is the actual one that flew. So look, there's 139 release mechanisms, hinge assemblies, motors, 400 pulleys. There's a 1/4 of a mile of cable in this. All that stuff had to work to make this sun shield actually work. So it was, when it worked, I think that was the thing that in that first 15 days that we all went, thank goodness for that this all came together. So this is 2018 early. So the telescope had now come back from its testing to Northrop, and Northrop was ready to assemble it to the what's called the spacecraft, where all the communications, power, control, etc. is, and to the sun shield, and with that end result there. So you just notice I said 2018. We'd committed to Congress that this was going to launch in 2018. So we had a bit of a problem here, because there was no way we were going to launch in 2018. So there was another painful review, not quite as at the same level, but it was clear that more funding was needed. So OMB and Congress were unhappy yet again. So we went back and said, we think we can do this for an additional 10%, $800 million. And they said, oh, okay. I mean, we've invested so much at this point, and you're not asking for a huge amount extra, so not like the DOD projects, the big military projects that we all see where the cost factors are 2 or 3 times. So they said yes. And so then for the next couple of years, there was just a great deal of good progress. So NASA sent a lot of folks out to Northrop, and it was fascinating to watch because the 2 engineering approaches were very different in many ways. And so there were different cultures for how do you do big engineering projects. Having people with those different cultures together struck me as an extraordinarily valuable step, because people ask questions. They see something and they say, why are you guys doing it this way? And they would explain and say, oh yeah, that sounds fine. Or, but that could lead to this. So there was this to and fro when we were dealing with a lot of very complex questions that really benefited from having the 2 groups together. So we actually delivered this within the budget. And so, as I showed you before, we were ready for launch, and the launch and commissioning all successful. And so the first science observations came about in July. So these were the big event. NASA loves to do a great big event with what they call early release observations. They get some really fabulous picture and shows that, yep, the mission is a success. And so they set up to do this, and I showed you the one before that was shown at the White House. The formal release of most of the images was actually on July the 12th, and so I was back in the auditorium of Space Telescope Science Institute. I realized sitting there, taking this photo, that 33 years before, we'd held the first conference in the big NGST conference in that same room. So we had 33 years of history in there for NGST and then Webb. And there's mission control at Space Telescope as well. So this was the image that was shown. This is I'm always amazed to look at this. Just incredible numbers of galaxies. Let me show you. So that little white thing up on the right is a galaxy much like the Milky Way. Okay, thanks, Anne. So this is like a giant cluster of galaxies. A lot of gravity associated with that. It's actually acting as a natural telescope, amplifying galaxies behind, and distorting them and all. But this is an incredible capability, mixing that with our Webb telescope. And as I said, this is the deepest image ever taken of the universe in the infrared. And in this image, there were tiny little red dots you can't see here that actually were objects that we now know back about 13 billion years, 95% through, and actually 97% through the whole life of the universe, and I'll show you a bit more of that. So, as I mentioned earlier, I think what Webb is doing here is it's really talking to us about and showing us about our origins in the broadest possible way, from the first stars, the first galaxies, how black holes developed and impacted things, how galaxies grew and changed with time, how the stars form during the life of the universe and planetary systems around them. It's starting to give us the opportunity to do that. So it has a huge bunch of science goals, which I laid out here, which I think we're really meeting. And of course, the discovery aspect is new things that we didn't really think we would, just to come out of left field. These are often the most important and interesting things in a mission. So I'm just going to flick through, since I don't have too much time left, a few images which were shown in this first period, which really still exemplify the power Webb. This is a star-forming region in our own galaxy. This is a nursery for young stars and planets that are forming in our own galaxy currently. These are just dramatic images. They did a great job. We've probably all seen this. The Eagle Nebula, Hubble on the left, Webb added to this with these rather remarkable and bizarre, weird images. But these are dusty regions of space with different gases involved that come up in different colors. So all about forming stars and planetary systems. We're deeply interested in planets around stars near to us. And one of the ways we do this is by looking at this light, the effect of the light of the planet moving in front and behind the star as it rotates around. So this is a capability that Webb is extraordinarily powerful for, because we can actually start to tell now. There's a lot of detail. Did I do something here? In the next one, which just is where you spread the light out and we can identify elements in the atmospheres of the planets around these stars. We're in the early days of doing this with Webb, and you'll see more in the media as new results come out. But this is going to be one of the great things from Webb, is seeing if there's evidence for life in some planets. Extraordinarily hard experiment to do. And of course, our solar system, we get these amazing images of the planets like this one of Jupiter. I mean, that is just beautiful. I love that image. And the detail that's in there. But then I think that this is what we ultimately always wanted, and I'll just spend a minute or so on this before wrapping up. This is what we really wanted to do with Webb, was to go back and explore at the beginning of time, look at galaxies in their formative years and their dramatic years as well. This is what galaxies do a lot. They collide, massive galaxy car wrecks, and this is the way they grow and change with time. So one of the things what did I say? Oh, yeah. So one of the things, of course, was to see galaxies at the earliest times. And this we did within 5 days of the first science images coming out. There were 2 papers released and put available for everybody to see by 2 different groups. And we had found a galaxy more distant than any ever seen before, very close through 98% of all time, within a few 100 million years. Let me show you the next one. So the one on the right was forming 350 million years after the Big Bang, which was 13,800 million years ago. So you can see how close we are. The other one at 450 million years, looking back through 97% of all time. So Webb immediately demonstrated that it was going to be in a position to tackle that primary goal. And so we don't know what's going on there. There's a lot of unusual things happening with these early galaxies. There's a lot of black holes that we sort of didn't expect, brighter and more massive. The galaxies are brighter and maybe more massive as well. So the theorists who try and understand what we're seeing are having a field day with lots of different ideas and so on. So, you know, this is a year and a half ago where we first did this. We're still trying to get the data, and we're still trying to understand what the universe is telling, or what Webb is telling us about the universe. Okay, so let me wrap up here. So, of course, you know, Webb is an amazing cultural phenomenon, and this just struck a lot of us when we saw it. It was put on social media, Halloween 22. This young woman in Salem, Massachusetts, put on this Webb costume and posted it, and I thought, this is incredible. You know, people see this, they like what it's doing, and they get really enthusiastic about it. So there's well over thousands of papers now that have come out, and I think we're all trying to come to grips with that. But one of the things I wanted to wrap up with was to thank Wendy, my 55-year spouse, who has been a great companion and really helped me. I couldn't do these things without her. And so, just to wrap up then, here is, I think where we're at. We have a cosmic telescope that will reveal an amazing amount about the universe and about our origins. So I think of it as our Cosmic Sunrise Telescope, and I'd like to thank you all for your interest in Webb and in the science as well. Good. Thank you. Thank you very much. You're going to do the questions at this point? Thank you very much. Yeah, it made me cry, I have to tell you. Your slides are good. Yeah, good. Thank you. Yeah, it was interesting because I think the feedback very good. Make it live. Yeah. Well, thank you. That's good. Uh-huh. Well, I do have another lecture in 2 weeks. I have another one this Thursday. Let's delay the Thursday one, so I can time to win here. Yeah, Thank you. Let me turn my mic on. Somewhere here. Is that working? Yes, that's working again. So while I'm looking at this, I can quickly answer a couple of these. James Webb was the administrator of NASA at the time of the Apollo missions. And so he deserves a huge amount of credit for the success of that activity. And so he was there during much of it. And the administrator in 2002 really respected him a lot. And so that was why he named it. And most of the scientists were very unhappy, and a lot of the people at NASA were too, because the tradition had been to name the telescope later when it was ready for launch. But anyway, so that was who James Webb is. There's a question about funding. So the vast majority of the funding was from the US, $10 billion, probably $1 billion from ESA and Canada, together the European Space Agency and the Canadians. That's a substantial contribution. They contributed the rocket, which was a big contribution for Europe. So while their part of the total project was small, it was still just very central and very important. So and one of the instruments is from Canada. The ongoing funding is actually about $200 million a year, and that comes from Congress pretty much. So that funding is really all the US to keep Webb operational. Let me see. So Kourou is a launch site on the equator, and you want to be close to the equator because you get the best boost, as it were, from the Earth rotation. That's why Cape Canaveral is pretty close and is in the south. So launch sites are always as close to the equator as they can. So Europe is a fair way north, so that's why they chose one of the French colonies, as it were, to put that site. Yes, this is an interesting question. So the likelihood of anything big hitting Webb out there, an asteroid, is extraordinarily low. But there are micrometeorites out there, so the question is, what could hit Webb? And we always knew that micrometeorites could actually whack Webb, and we expected little hits every month pretty much, and they're tiny. They don't really do much. Maybe put a hole in the sun shield, but it's got plenty of margin. The big concern is some of the bigger particles could actually do physical damage. And we know from satellites around the Earth they're fairly rare, and so we calculated probably we'd get hit by one of those every 5 years or so, and they could do some damage. So 4 months after we launched, we got whacked by one of those. And so everybody is going, oh dear, what happened? Did we get the calculation wrong, or what was going on? And it did some damage. It hit one of the mirrors and left a dent in it, and we had to sort of, as much as we could, reorient the mirror to minimize the effect of that. It had a discernible effect. It reduced the optical capability by the precision by about 10%. So if you get hit often by these, if we were going to get hit every 4 months or a year or something, that was going to be a life-limiting factor. So it's now been a year, almost 2 years, and we haven't had another big hit. So this is one of those weird statistical things. Once every 5 years, it could happen in the first month or the last month or any time in between. And it happened early, and so luckily, maybe our 5-year number is okay. So I'm not too worried about those particular issues. A quick question about the images. So the color on the images. So we take images which are essentially black and white images in a given filter. So take a red image, which is just black and white image, a green image, and so on, just like your phone does actually. It actually puts these things together. So we actually take the multiple images that we've got with different filters and make them look as though our eyes would see them in the infrared. So it's maybe a little unrealistic in some sense, but it means the shorter wavelengths are blue like they are in the blue, longer wavelengths are given a redder color, and so they are sort of equivalent to what we might see if we had infrared eyes. But yes, they are not sort of precise in the same way that you might think if you look at a Hubble image, which can be done so as our eyes would, if they could see it, would go, oh yeah, that's the way it looks. But so that coloration is very important. But of course, when we go analyze the data, we look at the individual results and work with that directly. This is a very quick one too. So the transit time to and from Webb. So I did a quick calculation in my head, and I think it's about 5 seconds each way. So about 10 seconds from the Earth to send commands up. And in fact, all the communications are done through the Deep Space Network. So slow commands can go up through that, and the data comes down through the very high bandwidth ones. And as I said, we have multiple gigabytes of data that come down. Yeah, this is, okay, let me just quick one here. So I think I mentioned this already. Yes, I did, about other countries contributing financially the $1 billion. And of course, they contributed technologically as well. Provided a very good rocket. They provided 2.5 of the science instruments. So the majority of the science instruments, the cameras and the spectrograph on this telescope are actually provided by our partners. So one of them was done jointly, and only one of the 4 major instruments was actually done in the US. So our partners played a huge role technically on this program, and we're invaluable for that too. It's interesting. So, we see a lot of political divisions these days. It's a horrible problem for us. And so somebody asked, do we see differences in regard to support? And my experience is no. I think science, we have got support across the spectrum. And folks are interested in, the US having a strong technological base, technological capability. It's good for sort of our standing in the world. And so there's just this broad support that if you do a good project, you do it right, you budget it right, you work it correctly, and you work within those frameworks, there's a general support. And we get criticism when things go wrong from Democrats and Republicans. So that is something that I have always been struck with in Congress. And so thank goodness that we can find that support, because it's lacking in almost any other area. Yeah, so there's an interesting question about why spend the money on this? And so this is all, and so, what do you get out of it? And I think the thing that I always say is we don't do this because we get the ability to do a new sensing system or some new medical technology. We do often. But I think this is for our culture, for humankind. We do this because we want to explore. We care, and we are interested in our origins. As I keep coming back to origins, it's sort of a universal, where do we come from? Why are we here? What happened? What came before? Where are we going? These questions are eternal and go across the human race. And so I think that for working those problems and just sort of working that capability, spending that money, it's money well spent. And so I just say, that's a personal judgment. You have to decide if that's the way you feel about it. But personally, spending, $500 million a year on a program like this, I think it's well worth it for the nation, and it's well worth it for humankind across the board. Okay, just quickly. Yeah, so question about how fast the distant galaxies are receding from us. And so they're approaching the speed of light. So if things get that light has taken 13 billion years to reach us. They're moving away incredibly quickly. And that's why we need a telescope like this, because it's really hard to measure these things. I think at the end you saw the little red dots that were all expanded up. They are really faint. And so, yeah, so the galaxies are moving away. So we're really exploring into the very distant past and into a frame which is, it's sort of hard to conceive that we're looking at something that's moving away incredibly quickly like that. But it is certainly doing that, and it's because we're looking so far back in time. So there was a related aspect here. So is there another project in the works? Well, of course. So in the 2020 Decadal Survey, astronomers said it would be great to have a telescope that could really detect life on nearby planets around nearby stars, while also being able to do a gamut of other observations. So that's the one that's currently before NASA and OMB and Congress. It's not going to get much funding in the near future. The money's very tight. There's another interim project which is being finished. But that's the one that's on the plate for the next 20 years or so away from now. Yeah, so just about something I would maybe just pull out the part of this, about the future. So, you know, will the universe collapse again, and will there be another Big Bang? You know, it's fascinating to get into these questions, because this is all to do with what dark energy is and its effect on the universe. And we don't know what it is, and we don't know what its effect really is over time. So we have some really imponderable questions. They're things that we just do not really understand. The dark matter you've also heard about, and I think the reality of that is well established, even if we don't know what it is. Dark energy is something that's definitely there and having an impact on us, on the universe at the current time, but exactly how that will play out and how it changed in the past, I think is still being sorted out and modeled and so on. So there's TBD, but yes, so the universe could certainly collapse again and was expected to go through that phase. But it's a long way in the future. I wouldn't worry about it. The sun will burn up the Earth well before that happens. Yeah, there's a... Okay, this is an interesting question. So I didn't quite get it at first. So if there is a planet around a star somewhere near us where we think there might be intelligent life, how long does it take us to communicate? Unfortunately, it takes a long time. You know, the nearest star is light years away, and that means that we send out a signal, and then years later, they get it and respond, and we get it years later. It's pretty rough holding a conversation with that sort of time frame. It's bad enough communicating with, you know, with the astronauts when they're on the moon. I mean, you get these horrible delays. So it's years, and the likelihood, you know, the typical star that might have intelligent life, I have no idea where that is in the galaxy or how many there are of them, presumably some. But communicating is a major challenge just because of that time frame. A typical star might be 1,000 light years away or more. So it's a 2,000-year round trip. So that is not going to be a great conversation, especially, you know, if we don't last 1,000 years or they don't last 1,000 years. This is open-ended. So it's a challenge communicating, that's for sure. Yeah, so it's hard to think about the universe. So the universe is really infinite. And so, but we can only sample a part of that because of the time it takes light to travel. And so the universe is expanding from the Big Bang, but it's everything. And so you can't actually step outside the box, as it were, and look at it. The only thing that's there is the box. So conceptually, this is just awfully confusing. So I, all find it confusing. I'm sure we all do. So it's very hard to think about this. And then there's also the questions that come up as to, is this universe unique? Are there other ones? And then the question is, can we actually find evidence for the existence of those? Is there any source of communication? And so we rapidly get into a very philosophical regime. If we can't get data, and we can't see a path to getting data, then it becomes very hypothetical. And there are indications in some of the physical theories that these options can exist, and so maybe they will exist, but it's not something that you can put a handle on or be definitive about. So conceptually, it's very hard to just deal with the fact that everything we see is everything, but not all of it. And we can't be out of it. So I'm sorry, I cannot give you a better explanation. Thank you.